looking at some more segments that come along with a triangle that are also concurrent lines when they are put in for all three parts. The first one today is a median of a triangle, which is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So it's going from a vertex to the opposite side, and where it hits the opposite side should be the midpoint. So B to F, F being the midpoint means that AF and CF are going to be the same length. Or A to D, making BD and CD the same length, because D would be the midpoint of that side. Or CE, E being the midpoint of side AB. So BE and AE would be the same length. And the point of concurrency, where those three lines intersect, is called the centroid of the triangle. So, and that centroid is always going to be on the inside of the triangle. Some of them go outside or on the triangle, but the centroid will always be inside. Doesn't matter what kind of triangle it is, whether it's an obtuse triangle, right triangle, or acute triangle. Always on the inside. And theorem 5.7, the concurrency of medians of a triangle, tells us that the medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So from the vertex to the centroid is 2/3 of the total length of that segment. So whatever the length of BF is, BP is going to be 2/3 of that length. And whatever the length of CE is, CP is going to be 2/3, which leaves PE over here to be 1/3 of the total length. So if this was a length of 3 from C to E, then C to P would be 2, P to E would be 1. Okay. And so forth and so on with all the medians. I forgot to erase this. So here C is the centroid of triangle GHJ, and CM is equal to 8. And remember, when there's not a line over the two letters, we're talking about the length of that segment. So this is read as the length of CM equals 8. Find the length of HM and the length of CH. So we're looking specifically at this median right here from H to M, and it tells us that C to M is 8. So that length is 8 right there. And remember, from the vertex to the centroid is 2/3 of the total length. And from the centroid to the side from there, then is 1/3 of the total length. So that tells us that CM is equal to 1/3 of the total length, which is HM. So we plug in the number there. CM is 8, so 8 is 1/3 of HM. So to solve for HM, we would divide by 1/3, and when we divide by a fraction, that's the same thing as multiplying by its reciprocal, which would be 3/1, which is the same thing as just multiplying by 3. So 3 times 8, or 24, is going to be the length of HM. And then CH, from the centroid to the vertex, we said that was 2/3 of the total length. So CH is 2/3 of HM, 2/3 of the total. And if HM is 24, then CH is going to be 2/3 of 24. If we multiply that out, that would be 48/3, or 16. and we want to find the coordinates of the centroid P of triangle DEF. So we got triangle DEF here on a coordinate plane. We're wanting to find the coordinates of P here, which is somewhere between 4 and 5 on the X. We should be able to see pretty clearly that it's on a horizontal line with D and G. Since D is at 2, 3, we know the Y coordinate is going to be 3. All right. So our Y is going to be 3 here. What we've got to figure out is what's the X coordinate? How far between 4 and 5 are we actually at here? So we know what D is. It's 2, 3. And G very clearly is at what looks like 6 on the X and 3 on the Y. And you know, we won't always have the possibility of it being perfectly at an intersection where we can see clearly where it's at. So had this not been clearly marked there, we would know that since this is a median, it's coming from the vertex to the midpoint of the other side. So we could have found the coordinates of G by using the midpoint formula, right? If we remember the midpoint formula, x1 plus x2 divided by 2 and y1 plus y2 divided by 2. So for G, we would have been using the coordinates for E and F. So the x's would have been 8 and 4. So 8 plus 4 divided by 2. And the y's would be 5 plus 1 divided by 2, which would have given us the coordinates 12 over 2 and 6 over 2. Or simplify those two fractions and we get 6, 3, which is exactly what we got by looking at it. But in the event that you can't just look at it and know what the coordinates are, that's how we would find the coordinates of that point. So we know that D is 2, 3, G is 6, 3. So the total length of DG, since it's a horizontal line, we can just look at the difference between the x's. So the length of DG is 6 minus 2, or total length of 4. So the whole segment, this whole median, is 4. We're trying to find the coordinates of P. So we know that from this point D to P is 2/3 of the total length of DG, or DP equals 2/3 of DG. And we know what the length of DG is, it's 4. So we're looking at 2/3 of 4, which is a length of 8/3. So our distance from D to P is 8/3. We're trying to find the coordinates of P, so that 8/3 is in addition to what the x coordinate was of D, which is 2. So to find the actual x coordinate of P, then we're going to have to take the 8/3 here and add it to 2, which when we're adding it to 2, we got to have a common denominator. So I'm going to put 2 over 1, and then we multiply the 2 by 3, top and bottom. So this becomes 8/3 plus 6/3, which is going to give us 8 plus 6, which is 14/3. So our actual x coordinate from 0 to there is 14/3. So our coordinates for P is going to be the x value, which we just figured is 14/3, and the y value, which is 3. So 14/3, 3 is going to be our coordinates there. Finding the 2/3 of the length of DG, and then adding that with 2 gives us 14/3, which if we divided that out, we put it into a decimal form, we'd have 4 2/3 or 4.66 repeating. So a little past 4.5 is where that is, which makes sense by where we look at it right there. All right, so now another segment that we can look at in a triangle called the altitude of a triangle. It's a perpendicular segment from a vertex to the opposite side or to the line that contains the opposite side. An altitude can lie inside, on, or outside the triangle. So what this is saying is to go from a vertex to the opposite side and to be perpendicular to it, to intersect that opposite side at a right angle, sometimes you won't always be able to go to the actual side. Sometimes we may have to extend a side of the triangle. Make it a little bit more drastic. So we had a triangle here, and I wanted to go from vertex A to the opposite side to form the altitude. To come to this side here, I can't come straight from A to the side inside the triangle and create a right angle. So what I would have to do is extend this side going this way so that when I come from A, I can come straight down and create a right angle there. So that's why it says from the vertex to the opposite side or the line containing the opposite side. Because it's possible we may have to extend that side opposite the vertex in order to create a perpendicular line going from the vertex to that side. So the orthocenter is going to be the point of concurrency for all of the altitudes. And the line based on the concurrency of altitudes of a triangle, the lines containing the altitudes of a triangle are concurrent, right? Just like all the other segments we've looked at so far. So if AE, BF, and CD are all altitudes of triangle ABC, then lines AE, BF, and CD intersect at some point H, which AE is an altitude here going from A to E, intersecting at a right angle. And this one we didn't have to extend the side because we could go straight across. But then going from vertex B, we had to extend side AC out so that we could create a perpendicular line to it, intersecting at F, creating a right angle, and extend it out so that it hits AE out here outside the triangle a ways. And then same thing with going from vertex C to its opposite side, which would be AB. So we had to extend side AB out so that we could intersect it at a right angle. And all three of those altitudes intersect way outside the triangle out here at point H, but that is a point of concurrency. They all intersect at the same place. So here we want to predict where the orthocenter is going to be located in the triangle. So we got three different triangles ABC. And so in this case, if the measure of angle A equals the measure of angle B equals the measure of angle C, we get an equiangular equilateral triangle. And so in this case, if we draw in the altitudes, and I'm just kind of freehanding it here, doesn't have to be exact because we're just trying to determine is it going to be outside inside or on the triangle. So just drawing in what looks like it would be perpendicular to the other side. And when I do that with this first triangle ABC, we can see that the orthocenter is clearly on the inside the triangle. All right, B, if the measure of angle A equals the measure of angle B equals 45 degrees. So we're saying we got 45 degrees at A and B, which 45 plus 45 is 90. So that leaves angle C has to be 90 degrees or a right angle. So if I go from point B to the side opposite of point B to intersect that side at a right angle, then I can just follow straight down side BC, because I'm going from B and I'm hitting side AC at a right angle here, because there's a right angle at point C. Same thing with going from A to side BC. I'm going to go straight down the side AC because I'm already hitting that side at a right angle with that side. And then the last option is going from C to the opposite side to hit it at a right angle. So when I do all of that, my orthocenter is right there at point C, at that vertex. So since it's on the vertex, then it's on the triangle. And then with B here, or with this triangle BAC, if the measure of angle A equals 110 degrees, so we got an obtuse angle right here, right? And so we should be able to go from side A straight across to side BC and hit it at a right angle. Now if I want to go from B to the opposite side, in this case I'm going to have to actually extend this side out a little ways. So that I can come straight down from B, hit that side at a right angle. And likewise, coming from point C to side AB, I'm going to have to extend that side out a little ways. So I can hit this side at a right angle, which at this point, I don't have a point of concurrency. There's none of them are intersecting. So I'm going to have to go ahead and extend those lines out further. And when I do that, I see that they all come together way outside the triangle over here. So here's my point of concurrency, and it is definitely outside the triangle. So basically what we'll see, what we're kind of seeing is that with an acute triangle, it's on the inside. The right triangle, it's on the triangle. And with an obtuse triangle, it's outside the triangle. And that finishes the notes for today.